All right. So today is one of the more dramatic lectures, I think, because we're going to try to do connectivity in logarithmic space, but without any randomization, right? So we've been doing a lot of random walks. Skip this. Yeah. So here was sort of this thing where we did connectivity in log n space. Um, but the algorithm was pretty simple. You just randomly walk around. You don't only need to remember the index of the vertex you're at. That's log n space. And by a bizarre connection to electrical networks, um, you can actually show that you'll probably reach T if they are connected in mn steps. You can drive that error down by just repeating the experiment. So, okay. And since then, we did more random walk stuff, like we did this spectral theorem where we focused on the rate of convergence in an undirected graph to the stationary distribution. That'll be relevant today. We also talked about connections to conductance and low conductance cuts, okay, and connections between that and eigenvalues. So, okay, so today, again, the goal is to do deterministic connectivity in log n space. I think we'll definitely won't finish that today. And along the way, we'll have some interesting technical ideas. One is the idea of an expander graph, okay, which is like some secretly very important class of graphs. Another is this idea of a zigzag product, which is this very clever graph construction to pull some things off. And then for analysis, we're going to have to get used to tensor products. Okay, so we'll see what we covered. Yeah, fool you once, shame on me. Okay, I'm pretty sure you can solve the cat maze this time, right? But you're just trying to get from S to T. Right? BFS DFS takes linear time and space. Oh, this was last year's vote that I forgot to update, I think. Okay. So, okay, so this is what we did a few weeks ago, a couple weeks, I don't know, sometime before the solar eclipse. Basically because the cover time is always at most a polynomial, a random walk will hit T. And so the question is, can you do this without randomization? Yeah. So usually I ask for, well, maybe I could still ask, for those who haven't seen this before, does anyone want to suggest an algorithm? I have no idea, like, what the form of an answer to this question would look like, but sometimes it's worth appreciating how difficult it is. Okay. Good. So, right. So, okay. So, we know this stuff about stationary distributions and strongly connected graphs. And we also showed previously that an undirected graph always has a stationary distribution proportional to the degrees. Okay, so those are two facts. And we also know this convergence rate. So those are three things, okay, to keep in mind as I introduce expander graphs. So a graph G is called an expander if the spectral gap is at least a constant. So spectral gap is the difference between 1 and mu2 or negative mu n, right? So it really controls the rate of convergence of a random walk. Okay. So some people will write like a gamma expander for this parameter gamma. So I'll just say expander. That just means there's some constant. Okay. So that means you're convergent to stationary distribution, at an exponential rate, right? So it's a graph where a random walk starting anywhere mixes really fast. Yeah. So, okay. So I have two questions about expander graphs for you. One, can you think of a deterministic connectivity algorithm for a constant degree expander, if you don't know this answer already. So wrong answers only. Can you think of a deterministic algorithm for a constant degree expander? Let me ask a different question first. What is the diameter? So the shortest path from S to T over, but the biggest one. Okay. Why? Okay, so look at a random walk, right? The high level idea is the random walk converges really, really fast. So let's say the spectral gap is 1/2. Okay. So you converge to a stationary distribution, which is proportional to degrees at a rate of like 1/2 to the k times n. I feel like that should be square root n, but it doesn't matter too much. Okay, but it's dropping really, really fast. Okay. So if you take k to be like log n, right? Uh, well, okay, the L infinity norm, that's the maximum coordinate. That's bounded by the L2 norm. Okay, so I want to argue there's non-zero probability. Um, and this will be at most 1 over some polynomial in n if k is logarithmic. Okay, so if I look at any coordinate, like what are the odds of being at some vertex t after log n steps, and I compare it to d over 2m, that's like at most 1 over m or something, right? Okay, that difference is at most the sum of squared differences, and that's at most 1 over poly n. So that means that rkx of t has to be at least 0, strictly greater than 0. Okay, so right? Uh, so there's a non-zero chance that in log n steps you're going to get from S to T, right? So all that matters is that there is a possibility. So there must be some way to get from S to T in log n steps. All right. So if you knew that, we come back to this question of getting a deterministic algorithm for connectivity on an expander. Let me ask one more baby question. If I wanted to do a random walk on a constant degree expander, how many random bits do I need for each step? Let's say the degree is 10. Yeah, right? Log of 10 or something. Yeah, probably 4. Okay, so what's great is that the diameter is really small, right? And that for each step, you only need to sample a constant number of bits, okay? And you put that together, how do you get a deterministic algorithm for connectivity and expanders? So what's the algorithm? Yeah, you can just enumerate all paths, right? So you can just say, okay, first step, I choose 1, 2, 3, or 4. Next step, 1, 2, 3, or 4. 1, 2, 3, or 4, right? So each step I need like 2 bits, and you make log n choices, right? So you only need to make 2 to the n possibilities. So you can just enumerate all the paths of length log n in just a big loop and see if any of them reach t. Yeah. Really upper bounded. Well, it's still an expander, so there's probably no degree 1 expanders or degree 2 expanders because an expander has, yeah. So maybe that's also an interesting tension, right? So there's a question about whether there exist constant degree expanders, right? Because these are graphs that have very low degree. So a very high degree expander is just a click, right? One step you can get anywhere. That's not very interesting. So the idea that you have a very sparse graph, say degree 10, there's only 10 n edges, but you can get anywhere in log n steps, right? So that's like a very nice graph. So it's a graph that almost, when you say that it converges to a stationary distribution really fast, especially a uniform one, then it's really like a click. A random walk is not that different than a random walk from a fully connected graph, which would have been completely random, right? So these are graphs that are intuitively really, really well connected, but somehow using the extremely small number of edges, they're extremely sparse. Okay? So I think, do you guys have a homework problem on constructing an expander? Okay, well that's a good one. These graphs do exist, and one of the potential homework problems, otherwise exercises, um, will ask you to make one. At a high level, you can just take actually three uniformly random matchings in their union. That makes sense. Will be an expander with some probability. Okay. So obviously that's like a very low degree, right? So three matchings is like degree 3 or something. You might need more than three matchings, but just a few matchings basically. Um, and it'll have this sort of it'll seem to get this best of both worlds, where the graph is extremely sparse, there's very little information, right? And yet extremely well connected. It's really almost like a click from a random walk point of view. So part of this lecture is about appreciating the existence of these objects and the surprising results they lead to. All right, so that's what we showed. In a constant degree expander, with constant expansion, it's actually not that hard to get log n space connectivity because you can just enumerate all paths, right? It's almost lame. Like, okay, just enumerate all paths. So, good. So, what's here? Okay, so what we're going to show then today, and it's a relatively recent thing, is how to get log n space for any graph, even if it's not an expander. Okay, so expander graphs, actually, this is not so bad. The difficulty here is, can you do this in a non-expanding graph? All right, so okay, so here's sort of yeah. No, the graph can be any degree, but we can address that right away. So I claim to you that we can always turn an undirected graph with high degree into one with low degree. It's a little trickier in log n space. Well, I think we're going to assume low degree, and it's not hard to do the reduction, but it'll come back to me later. Okay. It'll either come back to me or it'll fade from your memory. Okay. But let's assume the input graph is undirected. High level, so to take a high degree graph and turn it into low degree, you just split the vertices up, and then you have to be a little bit clever about how to do this in log n space. So I'm guessing if you have edges like numbered from 1 to n, the first 4, second 4, third 4, you just need some schema, to be able to do this implicitly in log n space. I think it's not that bad. So the high level reduction is if you have a high degree or input graph G, split the vertices so you get low degree. The number of vertices doesn't change that much, right? The only annoying thing is you only have log n space total, so you need to be able to do this implicitly, which I think is not that bad. So you just imagine okay. Okay, it's doable. It's just tedious. Okay, it's fine. All right. Okay. So the high level idea, you give me any graph, and step 1 is we're going to convert the graph into a constant degree expander. Okay? And then what's step 2? And then you just enumerate all the paths. Okay? So, so it's not such a bad, tough algorithm once you get through step 1, which is just the pre-processing step. How bad can that be? You just enumerate the paths. Okay, so same high level idea. So the idea then, somehow we're going to try to implicitly convert G into a constant degree expander. So yeah, we just have to check that our construction works. But remember, you're in log n space. So we can't actually like make a brand new graph. So the graph things we do are going to be kind of clever in a way where you can sort of simulate some of these changes without actually constructing the whole graph. And we'll talk about that when we get there. But then you'll have sort of oracle access to a constant degree expander, and you can do a random, I mean, you can enumerate walks on this expander. Enumerating walks on this expander, underneath all of those graph transformations, will be doing some kind of walk in the original graph. Although it's hard to think about it. Okay? And so somehow, at the end of the day, I think you are, underneath the entire reduction, going to be enumerating paths in G, the original graph, in some kind of exhaustive way, as if it were an expander, without it actually being an expander, right? So this is just like complete nonsense. This is like completely crazy, okay? Like, doesn't make any sense, but it's gonna work. Okay. All right, so here are our two graph transformations, which will apply implicitly. Anyone want to guess one of them? Yeah, one will be the zigzag product. Unfortunately, that's number two. Anyone want to try to guess what number one is? Because the white squares can only be removed in order. Yeah. So one step is going to be powering. I'll explain that in a moment. The other one is going to be this mysterious zigzag product. Okay. Like many things in TCS, we give the most intimidating possible name to something, and then we'll spend all class trying to unravel and remove the stigma from the name, and then it'll make sense. Okay. Okay. So we're just assuming the graph is a constant degree to start. Okay. But again, this is just coming from splitting high degree vertices, and then you just need to do that implicitly. It's not so bad. Okay. So powering, okay, just means that the second power is like I'm going to take every consecutive pair of edges and replace it with the edge connecting them. Okay, so G squared is going to like have edges corresponding to 2 hops. For some reason I thought literally hopping would help. 2 hops in the original graph. G cubed will be 3 hops. G to the K will be K hops, right? G to the hip will be G to the 3 would be 3 hops. And yeah, G to the hip would be hip hop. Okay. So that's the idea. What is some intuition for this? Why might this be good? It's bringing things closer together, right? Or what about like from the random walk perspective, especially the analytical one? It improves the expansion. So remember, we always have those eigenvalues that are less than 1, and we're taking higher powers, and so it's getting further away from 1, right? So that's great. So what is, yeah, so the eigenvalues are kind of getting further away from 1. The spectral radius is increasing, so that's good. What is, so if this was so great, we would just take the log nth power or something, we'd be done, right? Okay, but so what goes wrong? Edges, and yeah, more specifically, like why can't I just take a high power for K and just run the algorithm? Uh, oh, no, it's not exactly K that's an issue, because I can also try all the Ks. But it's because someone else said the degrees are getting higher each time, right? Because each of my edges now gets multiplied by a number of edges on the other side, right? So the degrees are growing exponentially as well. So the spectral gap is good, but the degree increases from D to T, D to the K. Okay. Sure. So G squared is enumerating all the 2 steps, right? So let's say it's regular degree 10. So I have 10 choices times 10 choices. So now the degree becomes 100 because I have in G squared, it's all but two steps. Okay. All right. So the point of the zigzag coming up then is to try to figure out how to fix the degree. Okay. Okay. So here's sort of a high level idea. So let's let G be a D-regular graph where D is a little bigger than we would like. Okay. And at a high level, like one way to think about it is like, okay, taking a random step in G would take too many bits. Okay. So the question is, how can I simulate D choices with much fewer than log D bits? Yeah, you want to kind of reuse some of the bits, right? So what if I told you that the solution somehow involves expanders? This is supposedly an expander graph, by the way, if you Google expander. Um, so suppose you have access to, you can build graphs like this, graphs that, are well connected but very sparse, low degree. Imagine D is moderately big. Suppose I made an expander with D vertices. Suppose I had an expander with D vertices and degree 3 in this picture. Number of nodes in G never increases from powering. Well, it's bound by N. So we want to keep things constant because we want to get back to the strategy of, oh, once things are constant, I can enumerate all paths. Okay. So let's say I had D vertices in this expander. Okay, so 1, 2, so on and so forth, D. And the degree is like some constant D0. Okay. Now, intuitively, if I take one random step, and I do this a lot, so this will kind of go back to this idea of reusing randomness maybe implicitly. This next step should sort of appear random from a certain zoomed out point of view. Okay? So if we just for the moment, like there is some difference, this is not a complete graph. One random step couldn't necessarily take you anywhere. But in a certain aggregate sense, we know that several steps rapidly approaches the stationary distribution, right? So sequences of steps in this graph sort of look like a random walk, okay? So one intuitive idea is this. So the issue is that I'm trying to make one of D choices. D is too big, okay? And I want to kind of reduce the number of choices without really losing all the degrees of freedom. So you'll start at one choice out of D, and you'll take a random step to your next choice. So you only need, log 2 bits to choose the next neighbor in here or something. And that'll get you to a different choice out of D. Different choice out of D, different choice out of D, different choice out of D. So you're just taking a local walk in the expander, and it's giving you different choices out of D in the original graph, right? So I'm going to try to simulate. I want to do something where a random walk in G sort of like, oh, take a random step in the nice graph. It's like magical dice where you can get almost random numbers without fully rolling the dice. And then use that to choose my next neighbor in G. Okay. Now it's not fully random. Being here and going there, it's going to limit the choices to some extent on the next step, on the next step, on the next step. So it's not exactly the same. But in the limits, right, sequences in this graph really start to look uniformly random if we believe this math about approaching a stationary distribution. So you're hoping that maybe in some aggregate sense, your pseudo-random walk in G, you're not doing a fully random walk, you're using fewer random bits and you're pumping it through your magical expander to choose your next vertex, but you're hoping that it sort of behaves like a uniformly random walk. Okay, so you have this sort of like magical dice where it is true that the next step is not that random given the next one, but over many steps in the aggregate, it becomes more powerful because it mixes. Okay? So we need to translate that to some real analysis to prove this, but that's the idea. Okay, so it's a very nice idea. Yeah. So you're at some vertex in G, right? So you're at this vertex, which corresponds to this choice, and it doesn't, well, let's just say you're there in the graph. It's slightly different. And you pick a random vertex here, right? And this is some index, I out of D, vertex I in the expander graph, right? And so out of the D many neighbors, there's D of these neighbors. You're going to pick the ith one and go there. Okay? So you take a random step in your auxiliary graph, truly random, but you're only making one of three choices in this picture and one out of constant in general. Okay? That gives you some index out of D, like 10, and then you're going to choose the 10th neighbor in G. Okay? And now, for your next choice, right, you're here, your last choice was this one, and now you're going to move to another vertex like this one, okay, and this will give you some index J, okay, and okay, this thing has D neighbors, okay, there's D of them, and one of these is number J, and you're going to go there. Well, this step is truly random, right? So if you knew where you were in this graph and where you are here, you can actually only go to 3 of the neighbors or something, right? So you're not really in a single step considering all possible neighbors of J, of I, when you chose J. So what you're gonna be maintaining two states, right? So think of like some kind of random number generator on the side. That's your second state. But what you don't know is your random number generator isn't that random. It's maybe coming from this phenomena here. So think of this as a random number generator between 1 and D, which if you zoom out, you can't really tell it's not a perfectly random number generator because it seems to look like the stationary distribution. But if you had looked under the hood, you realize, oh, okay, there's actually not much going on here, right? Because it's just a low degree expander graph. So at any point in time, you have your current random number generator and your graph. Okay? So you just punch the random number generator, choose your random number between, look, you think it's random between 1 and D, and you go to the corresponding neighbor in G. And internally, the random number generator did not actually use log D bits. It used 2 bits. Okay? Yeah. So what we're actually going to use this is where we haven't quite got there yet. So the high level idea is we haven't even actually shown how to take G and reduce the degree. This is still just kind of building some intuition. So what's going to happen is that D is going to get moderately big to like 1,000,000. And then we're going to reduce it down to like 5 with this construction. So, and then it'll blow up to 1,000,000, get it back down to 5, blow up to 1,000,000, get it back down to 5. And we're hoping that at a high level, we're going to power up, improve the spectral stuff, and then but the degree goes up to like a million, and then we're going to bring it back down with this idea. We have to turn this into a graph, but it's going to be basically the same idea. The graph will allow us to simulate this. And what's the point? The spectral gap will get a little worse. We will give up something because this is less random than the original random walk, but we'll show that if this spectral gap is good, it'll be a net win. Now, as for your question, how much space does this take? Well, this will take big O of 1 million space because there's 1 million nodes. So it's a big constant, but it's still a constant. So we're okay with that. Yeah. 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 Yeah, you can think of this as a pseudo-random number generator for your graph to do your random walk. However, I think we'll see in a moment when we do the analysis, it's going to be very convenient. This is a graph and stuff because we can look at the spectral gap here, the spectral gap here, and actually calculate the spectral gap of this combined thingy. So it will eventually be helpful that we understand the mechanism for this pseudo-random generator, but its purpose is sort of like a pseudo-random generator. Yeah. Okay. All right, so here's the full details. But let me explain this. So G is my D regular graph, and H will be my expander with constant degree. Okay? So what you really want to do is you want to take a step in your expander, right? So you take a step in your expander, and then that step dictates a step in your graph. Okay? The only issue is that's not symmetric. If you drew those edges, so you can have a so you make an auxiliary graph where at any point you have a vertex in your original graph, a vertex in your pseudo-random generating graph, number generator graph, right? So you take a step in H and that moves you in G, okay? But if you drew those edges, you won't get an undirected graph. It's not symmetric, okay? So we have to add a couple steps to make it symmetric and like reversible so that the overall graph will remain undirected. And we could keep using all those spectral theorems and stuff that are our only hope to analyze this thing. Okay, so the first step, you move in H from I1 to K1 to its K1th. Yeah, okay. So the point is that ultimately the number of edges in our graph is going to be, or the degree will be D0 squared. So if the expander graph had degree 3, it's going to be 9 because we're going to roughly take 2 steps in the expander. Okay. So the first step, I'm calling that, okay, you go to the K1th neighbor. So I take a step in the expander from I1 to its K1th neighbor, I2. Okay, so that's the step in expander. And then in the graph, I move from V1 to the I2th outgoing neighbor of V1, which is V2. Okay. So that's the first 2 steps. And now to reverse it, okay. So I went from V1 to V2, and V2 was like the 10th neighbor of V1. And now I look at V2 and look at V1 and say, oh, V1 was the 15th neighbor of V1. Okay. And so now I'm going to take my vertex in H, and I'm just going to teleport to 15. Okay, so I'm going to move from I2 to I3. These are vertices in H, where V1 is the I3th neighbor of V2. It sounds confusing, but remember, the only goal is to make this operation symmetric. So if you just think it through, this is the only thing you can do. Okay? And then you're going to move from I3 to the K second neighbor. You're going to take one more step in H. Okay? So you take a random step in H, or you take a step in H, use that to move in G, and then you look backwards to move in H. Okay? And then you take one more step in H. So really, there's only 2 degrees of freedom. Your first step in H and the final step in H. Because once you make the step in H, then your move in G is based on H. And then your teleporting in H depends on G. So those next 2 steps are deterministic. That's, I guess, where the zigzag is coming in. Then you take one more choice where you take a step in H. Okay. So if H had degree 5, there's a total of 25 choices based on your first and second choice. Okay. Now your movement in H is kind of crazy because you take a normal, you follow an edge in H, and then you're going to get transported based on G, somewhat arbitrarily. You can hop to another side of the graph, and then you'll take one more step in H. Okay. So the back end, again, the point is just to make the whole initial first two steps, which are totally intuitive, by now at least, symmetric. Okay, so this is reversible. Okay. All right. Where do you store this H? Anywhere you want. In your pocket. So, because H is constant size. So, G has degree D, which will be a large constant. So the graph is going to, our overall algorithm, we'll put it all together in a moment. It's going to go back and forth between high constant degree and then low constant degree. High constant degree and low constant degree. And so this is at a stage where G has high but still constant degree. So H, will just have 100 vertices if D is 100. Well, D is initially constant, independent of N, right? So for starters, there's a constant. Our powering is going to make it a little bit bigger. And then we're going to use this to bring it back down. It's going to go back and forth, back and forth. But that will be a tension. Yeah. 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 So now every time you have an edge in this direction, in those between those crazy auxiliary states, you'll have an opposite edge. Yeah. So it makes the steps reversible. So for every edge, you're going to generate an opposite edge. All right. Good. Good. Okay. Any questions? It's appropriate to be confused here. Um, and it'll make more sense, I think, as we get into the analysis, we can see some of the ideas. The intuition, though, again, is we really just want to use H to simulate random steps in G. And it gets necessarily complicated, especially when we want to make it symmetric. Okay, but at least we know why it's complicated. And I don't quite know how to get around that. Okay. So, here is our lemma. The first two are pretty easy to see. So G was n vertices in degree D. So H has D vertices. At any point in time, my states consist of one vertex here, one vertex here. So I have ND vertices. Okay, so the graph gets a little bit bigger. And the degree becomes this expander constant squared. So D0 is something small and fixed, like 5 or 10. And I can always get it back down to 5 or 10 squared. Okay. And then this will require more work, but it actually says the spectral gap goes down a little bit. So smaller the better. No, bigger the better for spectral gap. We want a big gap, okay? So gamma G goes down from gamma G to gamma H squared, okay? So H will be an expander, so that'll be a constant, so it'll go down by a constant. So we get to completely reset the degree, but number of vertices goes up by a constant, the spectral gap goes down by a constant. Okay. So let's see how. Okay, so let's see how that works out. So I guess we'll just do one column of the table at a time. So let's say G originally had n vertices, degree D, and spectral gap gamma sub G or something. Okay? And we have G to the K, and then we also have a zigzag product between G and H. And then eventually we're going to combine that and look at the zigzag product of G squared and H. Okay? So, okay. So if the graph has n vertices, degree D is spectral gap gamma sub G or just gamma. All right, help me fill out this first column. So how many vertices does G to the K have? And what's its degree? Okay. And what's the spectral gap? Something like that. Okay. All right. Now let's say that G has n vertices and degree d. Okay. And then I'll let gamma sub h be the spectral gap for h. Okay. So how many vertices does the zigzag of G and H have? Sorry. And d, what's the degree? This d0 squared. And then what's the spectral gap? I guess it's gamma G, gamma H squared. Maybe I should have just left that and not erased it. That's what we had before, right? Okay, good. All right, so I think the interesting part is this bottom table where we combine these things. So let's look at G squared zigzag with H, right? So I take G, I take a product with itself, okay? And then I zigzag it with H. Okay. So how many vertices does this have? N D squared, because G squared has degree D squared, okay? And what's the degree of this graph? D0 squared. And then what's the spectral gap? Uh, should be like 1 minus gamma G squared times gamma H squared. Is that even true? You tell me. Gamma is the gap. So when we power G, it's the mu's that get powered, right? So that's 1 minus gamma that gets powered. So, okay, so what happens when we work this out? So we get 2 gamma G minus gamma G squared. Is that correct? Times gamma H squared. Okay, so we get 2 gamma G gamma H squared minus gamma G squared gamma H squared. Did we do that correctly? Did I do the math okay? Okay, so what's the point? So think of gamma H as really close to 1. Okay? And we could have made this constant K2 bigger by taking a higher power of G. Okay? But gamma, think of H as an expander, so think of it as really close to 1. So just for sake of discussion, imagine it is 1. Okay? Then you're going from gamma G to 2 gamma G minus gamma G squared. Right? So you're basically doubling as long as gamma G is smaller than some constant. Say gamma G is smaller than 1 over 100. Once gamma G is 1 over 100, then we can just enumerate everything in 100 log n steps or something, right? And get an n to the 100 algorithm. Yeah. So, so, so the dominant term is actually the 2. The factor of 2 would dominate gamma G squared, especially if gamma H squared is still much bigger than 1/2. Okay. So this is actually a net win to some extent, except the number of vertices did go up. So if you did this repeatedly, the degree stays fixed, so that's now under control. But the issue is that number of vertices does go up. So yeah, okay. So that's what I worked out. If gamma h is at least 3/4, then gamma h squared is 9/16. That's more than 1/2, so you'll make some progress. It just has to be strictly bigger than 1/2 for life to be okay. Okay. And yeah, so okay, so you can do this, logarithmically many times or something, right? And each time gamma g will go up by a constant. Okay, so maybe for the sake of concreteness, I'll just write 1.01 gamma g. Okay, for the point is it's going up by a constant factor. So if you do this like 100 log n times, gamma g is going to start at like 1 over poly n. It's going to become a constant. Okay. Now the vertices, the degree is okay. The degree stays d0. Okay. But what about the number of vertices? It'll be possible. So each time you're going to go up by this factor of d, and you're going to do it log n times. So your number of vertices is going to go from like n to like n to the d, but it's still polynomial in n. Okay. So it's going to actually work out okay. You're going to get there fast enough. Okay, so let me then just explain what we'll have to do. Next time we'll actually start doing some work. So first thing to address is, okay, can we simulate this in constant space? Or something, right? And the key idea here is that you don't need to write down the whole graph. I just need to be able to say, what's my fifth neighbor? What's my fourth neighbor? What's my third neighbor? Of the auxiliary graph via a constant number of queries to the subgraphs that it's based on. It won't be that bad. And then the more interesting thing, well, we'll start doing stuff like this, where we'll need to start looking at the random walk on the zigzag and analyze the spectral gap of that graph as a function of the spectral graph of G and the spectral graph of H. And then we're done. We're just done. So all that's really left is like an undirected spectral analysis on steroids. Okay. And then we'll use some nonsense notation like these tensor products. Because it turns out that captures this graph product correctly. Okay. All right. So that's what we'll do Friday. Let me get us back into the mode. So we're looking at connectivity in logarithmic space. Connectivity, of course, is easy. And there's lots of space, right? Because there's just BFS, DFS kinds of things. We showed how to do this randomly in small space by just doing a random walk. And in fact, random walks will tend to visit the entire connected component in polynomial time. And yeah, so, okay. So what's the point? Okay, so the high-level approach we're trying to take is inspired by just looking at expander graphs. So an expander graph is one where the spectral gap is some constant, which means it'll approach the stationary distribution very fast. So in particular, we're interested in constant degree expander graphs. And if I asked you, okay, can we do deterministic connectivity in a constant degree expander, then, well, you might notice that, you know that in log n steps, you're close enough to a stationary distribution where you could be at any vertex. Okay. So you have a non-zero probability of getting anywhere in log n steps. So the diameter is at most log n. Okay. Combine that with the fact that you're in a constant degree graph, so that like each vertex, I only have 5 choices or something. Okay. And you can just enumerate all the paths of log n steps in polynomial time. Okay. And that's it. So for a constant degree expander, you can actually just enumerate things, and you'll be okay. And you only need, yeah. So that's what we did. And so we're going to try to do something inspired by this approach, the high-level idea which we started out on. The real thing is we're going to try to take the graph and turn it into a constant degree expander. And in the second step, you can just do what we just did. So The two things I'll remind you was graph powering and the zigzag product. Powering, you're just trying to take G and replace it with G squared. So each step in G maps to two steps in G squared. Sorry, each step in G squared maps to two steps in G, right? So your random walk is getting a boost. Each step you actually get to take two steps. So you're going to converge to the stationary distribution faster. Your spectral gap is going to improve, okay? The only downside is that the degree does go up. So to counteract that, we have the incredible zigzag product. So a high level idea is this. You're worried about the graph's degree being too large. Maybe it's still constant, but now it's a large constant, okay? So take a random step in this graph will require a few too many bits, okay? So what we're going to try to do is roughly have a random, pseudo-random number generator that can output one of the choices, and it should look kind of random in the aggregate, but under the hood, maybe it's only using a couple random, much fewer random bits. Okay, you just have this like pseudo-random dice, and you roll it. It's not truly random, but you still follow what to do. And the way we're going to do that, the pseudo-random dice is going to be a low-degree expander graph with exactly D vertices. So if you have D choices, like 1,000 choices, so about 1,000 vertices, but maybe the degree will be something like 3. Okay. So the idea is I'm going to take a random step in my sparse graph. I only need log of 3 bits, so like 2 bits to take a step. And then, depending on the vertex I land in H, I can take that choice in G. Okay. And the intuition there is that, okay, you know, it can't be totally random because you're only using log, you're only using 2 random bits to make many more than 2 squared choices. But if an expander graph really does mix very rapidly, then when you do this many times, you know, the overall sequence of vertices should kind of look random if that's what, you know, it means to be. So you're hoping that kind of the trail, the sequence of paths this is navigating through G starts to look more and more like a uniformly random walk, even though it actually isn't. Okay, so when I say in the aggregate, where that's going to show up is in the analysis. That's where things kind of get aggregated. So, okay, so to break that down, so I really only described the first 2 steps. So the first step is you choose a neighbor in H, which is the constant degree expander. And based on where you land on H, you choose a neighbor in G. Okay. And then the other 2 steps just makes this process like reversible so that the overall graph, if you wrote out all the directed edges, will come out like undirected. Okay. So the other 2 steps are, well, okay, now you've moved somewhere in G, and now from the H side, you're going to say, well, based on where I now am in G and look at where I came from, if I came from the 10th vertex relative to where I am now, I'll move the 10th to the 10th vertex in H. The step is kind of confusing. And then I'll pick one more random neighbor in H. Okay. So definitely the third step is a bit bizarre, but I think you should just understand it as it's just trying to make things undirected so we can still do a spectral analysis. And let's hope that it's at least like net neutral for us. It doesn't hurt us. Okay. All right, so good. So, you know, the main thing we're going to do today is try to prove this. Well, it's easy to see that the degree is D0 squared because the only actual choices you make are the 2 steps in H. And D0 is the degree of H. The interesting part is trying to show that the spectral gap is gamma G, gamma H squared. So it's a little bit smaller. Okay. But you should think of gamma H as being very big because H is an expander. So hopefully that'll still be a net win. So in particular, we'll look at combining. So I'll take G and raise it to the 2nd power and then zigzag it with an expander. Okay. And the really big win is that, you know, you're going from gamma to 1 minus gamma G squared, which is roughly 2 gamma G. right? When gamma g is still pretty small because it's not an expander yet, the 2 gamma g will dominate gamma g squared, so it's roughly 2 gamma g. And once gamma g is large enough, then you're just done, right? So you're only worried about gamma g being small. And so you're going to take gamma g, you're going to roughly double it, and then you're going to give back a little bit because of gamma h squared. So if gamma h is something, if gamma h squared is bigger than 1/2, you'll make some progress, right? We only need this to be like 1.01 to get a win. Okay, and you can make this a little bit more dramatic. You know, I just did the second power for simplicity. If you do the third power, then you're going to be dominated by 3 gamma g, so you have a little bit more slack to work with and things like this. Okay, so really the powering is making a big progress because you're roughly doubling your spectral gap, and then you're giving back some constant from the zigzag. Yeah. No. So we're working. It's ultimately the total states it's like a product graph. There's, you know, at any time you have one vertex in each in the zigzag product, but the transitions are a little bit funky. Yeah. Oh, or a state like, so the product graph. I mean, every graph has some kind of. I mean, the zigzag represents some graph with vertices and edges. But a vertex in that zigzag product is really like one vertex in the original graph and one vertex in H. And then they move jointly, okay? But according to this zigzag step where I move in H, move in G, do the reverse moving thing in H, teleporting, and then move in H. And that will just be from one state to another. That looks like one step in the product, in the zigzag product, but it's broken in, yeah. Good. So, right, so that's just plugging in some numbers. Okay. So, all right, so this seems like sort of an involved, okay, so you can imagine taking G, taking H, and just building out this entire graph. But the obvious problem is that this is going to take a lot of space. Okay? And we wanted to do something that took log n space overall. So you can't build out the whole graph. We need to be able to navigate things implicitly, right? And so all we actually really need to do, because at the end of the day, I just want to be able to simulate a random walk in this graph, right? So I really just need to be able to answer questions like, wait, is there nothing here? Okay. So given a vertex V, what is the ith neighbor? Of V, right? So we're going to know like the overall degree in the graph is always going to be d0 squared after doing the zigzag product and things like this, right? So in our random walk, in the overall final thing, like imagine you did this construction all the way through, and then you're going to say, okay, give me a random neighbor, one out of the d0 squared neighbors, right? And you get some index I. And now you just need to figure out where you're supposed to go, right? So given this vertex where I am now, you need to be able to answer the question, what is the 10th neighbor? What is the 12th neighbor? And that's it. As long as you can do this and you get a new index for your new vertex, you're okay. So we just need to be able to answer these neighbor queries for both of these graphs. Okay? And they'll kind of build on each other recursively. So, right. So if I wanted to ask a question like, what is the I1, I2th neighbor of V in G squared? So, wait, is that correct? No, just ith neighbor, right? Okay. All right. The ith neighbor in V, and V is really a pair of coordinates V1 and V2, right? So that's going to break down into two queries. One, what is the ith? Oh, wait. No, it's just one vertex V. Oh, sorry. Okay, so, all right, the reason I want to think of it as I1, I2, so G squared has degree like D squared, where D was the degree of G, right? So I can think of D squared as just two choices, one out of D, right? So then you say, okay, first you say, what's the I1th neighbor? of V, and that'll return some, you know, V1. And then you say, what is the I-tooth neighbor or I-second neighbor? I don't know. Neighbor of V1, and that returns V2. Okay? So you really only need constant space plus the recursive calls, right? So imagine you have like a stack. So this is done, so this is in G. So this is going to be some kind of recursive call, right? I put this is on the stack, right? And then I'm going to do this recursive call, and then that's going to incur some space, and it's going to pop back out when I get my answer, and then I'll have constant space on the stack again. I'll do another recursive call, right? So your stack is going to look like, okay, you have I1, I2 written down, and then, you know, your recursive call is going to do a bunch of stuff here. It's going to use some more space. We'll figure out how to deal with that. But then you're going to get your answer. So now you have I1, I2, and V1. And your stack is you're going to get some more space from the recursive calls. And then you're going to output V2 or something, right? So, you know, you're really using constant space plus things from the recursive calls. And we're going to try to show two things, that all the recursive calls are all of the form constant plus more recursive depth. Okay. And scam likely. Okay. And then we're going to try to show the recursive depth is at most log n. Right? So why is the depth log n? Well, because each time I'm doubling my spectral gap in my construction. So if you start with like 1 over poly n spectral gap, which you can assume without loss of generality, you should only have to do this log n times total before you have an expander. Okay, so the depth will be okay as long as I can show that I'm always doing this constant overhead plus more from the stack. Yeah. Yeah, so I didn't quite make this clear, but so each time you do a zigzag and product, you're able to increase your spectral gap by some constant factor. So this might start at like 1 over poly n. And once you get it to a constant, you're done. So you need log base 1.01 of n, which is log 2 of n, up to a constant. Yeah. Why can you assume 1 over poly n? So all you need to do is come up with one vector where it's better, where the inner product is better. So I think you just take the random walk and you just apply the all ones vector on each side. And you should get at least 1 over n in every output. So all ones has Euclidean length n, and 1 over n will get you down to like 1 over n squared. So that's like n cubed already. You just need one test vector. Yeah. Yeah. So we haven't even finished yet. Yeah. Okay. So the first thing is, okay. So so this is just the powering. Okay. And so at least, hopefully you're convinced that the recursive stack should only have log n calls. So if I can show that both of powering would just be constant overhead, and I can show that the zigzag product will be constant overhead, then it'll just be constant times log n. That's the setup. So let's look at what is this? Okay. Oh. Okay, so this is the one for the zigzag product, right? So if I have the zigzag product, I need to be able to answer some kind of neighbor query, right? So again, the zigzag product will have degree d0 squared. So I can think of that as two choices out of d0. So I wrote k1, k2. And at any point in the zigzag product, you have one vertex in G and one vertex in H. And the vertex in H only takes log n space, right? Sorry, constant space. So, okay. So, you're going to first say, okay, what's the k1th neighbor of I1, and that's going to give you I2, right? So that's one neighbor query, which that can just be done directly. And then two, you're going to have to get the I2th neighbor of V1 in G. So that will be a recursive call to a neighbor in G. So that's when the recursive stack is going to start going again. And then that'll give you some V2. And now you're going to have to actually loop through because you need to figure out what index J so that V1 is the jth neighbor of V2, the backward step. So now you're going to have to loop jth neighbor of V2 in G until you get V1. But that's okay, that's a loop. And then the k second neighbor of this thing J would just take constant space. Right? So the nice thing about this space, which is a little bit counterintuitive because that's not how running times work, is that you only have to worry about the max. So if you have two different recursive calls, you're just worried about one at a time. They don't add up. So that's how this works. Okay. All right, so that's ultimately how you get log n space, because each time you're only doing constant overhead plus recursive depth, recursive space, and the recursive depth is log n. Okay, so yeah, so step three, you need to find the index j so that v1 is the jth neighbor of v2, and g still has constant degree, like d0 squared or something. So j should only take constant space. So I just say, oh, what about the first? What about the second? What about the third? What about the fourth? And I just loop through. So that's constant plus the recursive calls. Yeah. Yeah. So you're really making like d plus one recursive calls in this or something because there's d in the loop. But it's okay because there's only one at a time. Yeah, as far as running times go. Okay. Good. Good. Okay, so that's the issue of space. So you can actually navigate this crazy construction implicitly. Is really what's going on. Yeah. Yeah. So we never have to construct it. We just have to be able to answer neighbor queries. Oh, this is it. No, no. So you need to recursively call the neighbor in G. So you know where you are in G and H. H is constant size. H is a fixed known expander. The whole thing has 100 bits. Yeah. Yeah. So we're getting lucky here. Yeah. Yeah. Well, okay. So this is going to, G is really G squared, right? So then the recursive call, you're going to do this query. And then the G squared here, that's going to be squaring some zigzags in the previous layer. So then you're going to be calling a neighbor here. And then you're back in the zigzag product, and then you're going to look for a neighbor back in the power of the previous. So there's going to be layers, right? There's going to be like, let's call G0 my original graph. And then G1 is going to be G0 squared zigzagged with this constant expander. That'll give me G1. And then G2 is going to build on G1. G3 is going to be built on G4. G4 is going to build on G5. So you're really working like G log n, and you're trying to simulate a random walk on G log n because that's an expander graph. And so to figure out the 10th neighbor in G log n, you need to go down and figure out, ask neighbor queries in G log n minus 1, log n minus 2. So just to figure out the 10th neighbor in log n, you're going to have to go all the way down, and it's recursive calls, you're going back up, and this is not a fast algorithm. It's going to be okay. Because we're only worried about space, which is a little bit unusual. This form of thinking. Yeah. Okay. I mean, it's sort of an unusual question to begin with, right? Like trying to get log n space. It's not a natural question from any practical point of view. I guess it's a natural question from a computer. I mean, just purely theoretical, trying to figure out if space is a major limitation on computation, or how does space affect computation? How bad is the time complexity? I don't know. Maybe we can work it out at the end. Uh, yeah, I mean, it's only log n depth, and d is always a constant, so it's going to come out polynomial, I guess, because it's going to be like, t of where if k is the height in the tree, it's going to be like t of k is equal to dtk minus 1. So it's going to be like d to the log n kind of thing. So you'll get some n to the log d. Yeah. You're only using log n space, so it can't actually be that big, right? But it's not the fastest way to figure out if s is connected to t. Yeah. Okay. Good. So the key thing that's going on then is trying to understand the spectral gap of the zigzag product. Okay. So that was the key thing. We showed that we're going to try to prove that the zigzag product spectral gap is not much worse than the original graph. That's the high level goal. So I'm going to try to explain this notation more depth, but basically I can write it as a composition of 3 steps. The first step, I'll explain this notation in a minute, is that random step in H that keeps G fixed. Okay, and you can already sort of see this is sort of the identity is supposed to be keeping things fixed in G, and this is a random step in H. And the connection to tensor products will be clear in a moment. And then Z is actually doing a deterministic zigzag step, right? Based on where you are in H, switch in G, and then do the opposite thing. And then you do another random step in H. Okay. So a lot actually, it's going to basically come completely down to like, understanding these tensor things, which is a little bit of distraction, but hopefully it'll be okay. I think it's notationally a little bit more unusual, so it's a little cumbersome, but it's actually not that complicated. Okay, so, but maybe as a motivation, suppose we did something a little bit simpler, right? So we keep acting as if H is like is a clique, right? So let's just pretend it is for a moment. Okay. So let's say that S randomly samples a vertex in H. So that's like taking a complete graph and adding a self loop everywhere and taking one random step. So S will be like the all ones vector divided by D, which is the number of vertices in that graph. Okay. So what does this look like? So I would take a random sample in H, right? Pick a random vertex. I use that to take a step in G. And then I pick another random sample in H. So if I put that all together, what does that look like? What's the net effect? So completely random vertex in H. It's like a completely random step in G followed by another random sample in H. Okay. So in fact, this thing, which again I haven't really explained the notation yet, simplifies a bit. Okay. And so Okay, so what's the point? So random walk in G and uniformly random in H, this shouldn't really hurt your spectral gap. You're really just doing a random step in G, right? So your spectral gap should be the same. We'll formalize that in a moment. We're worried about losing, our spectral gap getting worse from the zigzag product. But if you were doing a completely random step over here, you wouldn't really change anything because you're still doing a random step in G and there's no information from the other side. Now, the high level intuition is that if we can argue that this is actually really similar to this because RH should be really similar to S, uh, then we kind of that's the high level approach. Okay, so we keep claiming that this expander should look like a uniformly random sample. And if that was actually true and I could just drop in S for RH, then we would get what we wanted. Okay, yeah. I guess it's not symmetric in that sense of the word. Well, it's just saying, well, we'll see, but like in a product graph of G and H, I guess it's slightly different than a product graph of H and G just because the names are switched, right? I mean, okay, so I is going to have the same dimension as RG. This is identity in G. But let's just talk about what this tensor product means because you haven't seen it before. Okay, so tensor product of a graph, I mean, if you map it to a graph, it's just going to be the product graph with product edges. Okay, so you have two graphs at any point in time, you have one location in each, and a step is a step in both at the same time. Okay, so we usually just call that a product graph, but I'm going to call it tensor product because it turns out like the random walks will map very nicely to certain tensor products. Okay, so we've already seen this a little bit before, right? These rank 1 matrices, one reason why I like this notation. So, you can take two vectors, right? And you can turn it into a linear map, right? So you can take Rn and Rn, and out comes a map from Rn to Rn. Or you can take Rm and Rn, and out comes a map from Rm to Rn. Okay, so you can actually do this kind of thing. And so that you already know. Now tensors of maps are going to be a little bit confusing because it's maps of maps. Okay. So if I have two matrices A in M by M space and B in N by N space, then A tensor B is actually a linear map from M by N to M by N. So it's going to, if you apply it to some M by N map C, okay, you'll get A transpose C, B transpose. Okay. In our case, A and B will always be symmetric, so transposes aren't a big deal. But it's a little bit weird. Okay, so equivalent definition. If you actually started from here and you worked your way up, is that if you apply A transpose B to C transpose D, the rank 1 map, then you always get this rank 1 vector. Okay. All right, that seems all weird. Just like there's some algebra rules, and you just try to stick with it. Okay. And because otherwise, if you blow this thing up and you try to imagine entries, if it's going from M by N to M by N, that means it's going to have like M squared N squared entries, and it's just like a massive pain. Like, just don't think about that, personally. So, just by working through this, okay, you can show that the eigenvalues, A has certain eigenvalues and B has certain eigenvalues. You might say, okay, what are the eigenvalues of A tensor B? And they're kind of what you would hope would happen. You'll get a bunch of lambda A's and lambda B's. Okay? And the eigenvectors will correspond to the outer product of an eigenvector from A and an eigenvector from B. Right? Because you can just imagine if C was an eigenvector of A and D was an eigenvector of B, and you plug this in, okay, you're going to get lambda AC and some lambda D. Okay? And then that would actually give you, M times N eigenvectors. And there's only M times N eigenvectors, so it gives you all of them. Okay? Good. So it's weird, but it's behaving nicely in certain ways. Um, yeah, so the special case that comes up for us uh, is this linear map. If I just plug in the definition, you get this. What's the point? Not sure yet. Um, okay, I guess these facts are relevant, but it shouldn't be too surprising. All right, let's see where we're going. Okay, so okay, all right. So I put this info in the bottom right, and at some point later, it'll be useful. Okay. So if I look at this random walk in H, we had the spectral decomposition. That's what we do in the first line, right? And we know that V1 is proportional to the degrees, so it's the all ones vector divided by the square root of the degrees, if you want to make the L2 norm 1. Good. So that would give us that matrix S that I mentioned before. So all ones divided by square root D, the outer product with itself, will give you like the all ones matrix divided by D. Okay, so that's like the random walk in the complete graph. Okay. Good. Uh, and if I look at like okay. So remember, gamma H is equal to the maximum of, I guess, 1 minus mu 2 and 1 minus mu n or something, minus absolute value of mu n, right? So what I could imagine is I could imagine like removing a small part of S so that like the coefficient in front of S would become the same as mu 2 to mu n. Okay. So then R sub H prime, all of the remaining things will have eigenvalues between, probably should be between gamma H minus 1 and 1 minus gamma H. Okay, so there's one eigenvalue of like value 1. If the next biggest in absolute value was like 0.8, so gamma H was zero point 0.2 or something, right? Then I'm just kind of removing 0.2 of the first eigenvector, setting that aside, and now this remaining spectral radius is 0.8. There's like 0, 0.8, 1 was my first eigenvalue, so I'm going to rip out 0.2 parts of the first eigenvector. Now now all the eigenvalues are at most 0.8. Okay. All right, so having ripped that out, let's see what happens. Okay, so let's look at this. So I've taken that initial thing and just substituted. I ripped out a small piece of the first eigenvector, and now all the remaining eigenvalues are between 0 and 1 minus gamma h or something. And I guess there's nothing to do but to just write everything out. So you'll get like ix r prime h, z, ix r prime h, plus gamma h times ix. All right, I think you guys can see which way I'm going, right? Gamma h times I tensor s z I tensor rh prime plus another gamma h, and these two will be reversed, z plus gamma h squared, and that'll give like two of these terms, z or something, right? This kind of thing, right? So okay, it's already done. All right, so this is just factoring the two quantities, okay? And so now what we're going to do is we're going to look at each of these terms by itself and try to bound the biggest eigenvalue and stuff like that. Okay. So good. Sorry? How do I know Z is linear? It's it's so it's the random walk map of our zigzag step, which is actually deterministic. So that means every column is just going to have 1, 1, and the rest will be 0. Well, just think of it as a matching. It just edges of some graph. And it's just taking one step in this graph. Yeah. And everyone has degree 1 because the steps are deterministic. Okay, so good. Um, okay. Well, I guess what we're going to do is, all right, these inequalities would be kind of be useful. So remember that trying to look at the maximum of AX is strongly related to the eigenvalue, right? So that's sometimes called the operator norm. You take a matrix A and you find the biggest AX. And if you work it through, you have some nice inequalities. This is like a Cauchy-Schwarz inequality. This is not too hard to show just by plugging in. And a triangle inequality. Just they're not hard to show one by one, but nobody wants to do that. Okay, I guess that's just going in the bottom right corner. Okay. Um, okay, so the real thing is let's just look at each of these terms one by one. Now I know the first vector eigenvector is all ones, so I'm going to be looking in the space orthogonal to all ones and trying to show that, you know, the second eigenvalue needs to be something. Okay. So, okay. So we already pointed out that this first term here, where I take a completely random vertex in H, do the deterministic zigzag step, and then another completely random vertex in H, we already pointed out that this is like a random step in G, right? So, right. So we put that together, and there used to be something here, but I can't find. Oh, there it is. Right. So we already know this to be true. Okay. Now the eigenvectors of the random walk in G and tensored with just a uniformly random S, right? They're going to correspond to eigenvectors in G times tensored with eigenvectors in S. And the eigenvalues are going to look like eigenvalues of G times eigenvalues of S. Okay. Now S is just a rank 1 term, right? It's the all ones vector scaled down. So the eigenvalues are just 1, 0, 0, 0, 0, 0. And then RG has some eigenvalues, mu1, mu2, mu2, where mu1 is 1, right? So the second biggest eigenvalue of the product, what's it going to look like? Just mu2. So the interesting eigenvalues of this are going to be mu1, which is 1, mu2 down to mu(n), and then a bunch of zeros. Okay, so this will have the exact same spectral gap as RG, which totally makes sense because you're really just doing a random step in G and the other one's already at the stationary distribution, right? So this one has spectral gap gamma G. Okay, good. Okay, so now this term. Okay, so let's good. Okay, so what we want to do, so we're going to work in the space orthogonal to the all ones vector in each component because that's the first eigenvector, right? So in that space, all of these random walks the operator norm looks like their second eigenvalue because I've effectively ripped out the first one. Okay, so good. What's the best way to do this? Okay, so if we look at the operator norm of this whole thing, sorry, it's a little bit analytical. All right, and I'm trying to find the operator norm. So I'm trying to figure out the x that gives like the biggest inner product kind of thing. So I'm looking at things like trying to maximize this subject to, you know, x orthogonal to the all ones vector in each one. How am I doing on time? Okay. So, okay, so the eigenvalues of this are going to look like eigenvalues of I. Those are all 1 times eigenvalues of RH prime. And RH prime, what were the eigenvalues? What's the biggest eigenvalue? Yeah, it's actually, yeah, or it's 1 minus gamma h because we ripped out a small piece. So you're going to get a 1 minus gamma h term here. Okay. What about z? So all you know about z is that it's a random walk matrix, although a very boring random walk matrix. Huh? Well, it's deterministic. That's what I meant. So it's not much of a random walk. Yeah, that's true. It's also very perplexing. Yeah. But it's deterministic. So yes, it's at most 1, just from being a doubly stochastic, stochastic matrix thing, not doubly. Uh, and then lastly, I tensor S. What are the eigenvalues of this? Yeah, most 1. So 1 times 1 minus gamma h. That's good. So this thing is at most, I guess you don't have to work in orthogonal to ones. Okay. At most 1 minus gamma h. Okay. Sorry? Just ignore this. Yeah, I don't think it's necessary. Yeah. Well, actually, it's already removed from RH. RH prime is removing some term. Yeah. Okay, good. Um, what about this one? This one reverses things. No, it doesn't really matter. You're just gonna be multiplying the numbers in reverse. 1 times 1 times 1 minus gamma h. Okay. And then, oh, that's not right. Well, this is gonna be tough to deal with. I think it might be impossible. Okay, one sec. Well, they're overlapping, so I can't rip one off of the other. If I select one, I'll select the other. So what we'll do? Oh, that would have worked. Yes. Yeah. iPad edit distance. Oh, that's the wrong one. So we want to do this, and I'll move this guy. Okay. All right. What about this? I guess this is 1 minus gamma h squared. 1 minus gamma h times 1 times 1 minus gamma h. Okay, so you start putting everything together, and so we already know that in our overall zigzag product, the first eigenvector is the uniform distribution because it's still a bound uniform degree graph. Okay, so we're working the space orthogonal to this. Okay, so This term, so this would be equal to, what was it? RG tensor S. Okay. So this will be at most uh, 1 minus gamma G. Let's say it has unit length. So it'll be at most 1 minus gamma G. Oh, yeah. So well, we will later, but yeah, in that scribble I didn't. Yeah. So and then for this term, this is at most, what do we decide? Gamma H times 1 minus gamma G. Is that what we did? Or was it 1 minus gamma H? Oh, it was 1 minus gamma H, right? Wait. Oh, yeah. 1 minus gamma H. Uh, this is at most, uh, oh, no, no. Yeah. I try to be massively inconsistent. And then you will learn by discerning the errors. Yeah. They actually train neural networks this way to uh, take one bad find neural network and then have a new neural network try to find the mistakes in them. Yeah. Okay. Um, huh? Yeah, yeah. I'm teaching adversarially. Yeah, yeah, yeah. This lecture is just a big GAN, and you will learn by discerning the mistakes. We should do that on the final exam. Just give broken proofs, and then you just underline where it breaks, and I think that would actually be a good exam, right? I'll just feed my lecture notes through a neural network. It'll flip some bits, and then you have to correct them, and that'll be a good exam, right? Because you don't have to memorize; you just have to find mistakes in logic. Okay, yeah. Uh, because I'm assuming x is already orthogonal to all one's vector. So I'm looking at the second eigenvalue of G. Okay, so what happens when I add everything up? So I get gamma h squared times 1 minus gamma G plus 2 gamma h times, I hope we land the plane, 1 minus gamma h plus, uh, oh, should the square be inside? Uh, because we should be looking at the second eigenvalue of this should be mu2 squared or mu n squared, right? So it'll be 1 minus, good question. Uh, okay, so if we look at, uh, okay, so this should be at most, oh, there should be a prime here. Uh, so this should contribute mu2 and this should contribute, mu2. So there should be mu2 squared, oh, which is 1 minus gamma h squared. Okay, something like this. Okay, that's fine. Hope we land the plane. Okay, what does this all come out to? I already found one. Okay, well there's gamma h squared, gamma g. Uh, No, the G is coming from this term. It's only because if I instead of using the real H, I had done a uniformly random. Yeah. Remember, because if H was a complete graph with self loops, then our quote unquote zigzag product would just be a random step in G. That's where that comes from. Okay, so if we add everything up, this is what we wanted, right? Okay, so this 2 gamma H times 1 will cancel out with a negative 2 gamma H here. And then you have this negative 2 gamma H squared, which will kill off the 1 gamma H squared getting added up. And then this 1 will become this 1. Oh, no, the 2 gamma H's. So here's another gamma H squared. There's 1 gamma H squared, 1 gamma H squared, and then negative 2 gamma H squared. So that'll kill each other. And then you're just left with 1, and then gamma G, gamma H squared. Okay? So we did it. And we didn't even use AMGM illegally. So that's great. Okay, so that's the high level idea. I mean, it's a little bit weird. I wonder if maybe the zigzag product can be reverse engineered if you were really comfortable with tensor products of linear maps. Because in fact, the eigenvalues are really well behaved and stuff. So doing these operator norms and stuff might be kind of weird. But if you did it for a living every day, it's not so bad. The rules aren't too complicated, and this is how it ultimately works. So yeah, you just trust the process, right? That's math. So, but that's it. So that's the full proof of deterministic connectivity. We didn't leave anything out. All right, thanks.